On the morning of July the 2nd, 2025, an explosion tore through a galaxy more than 5 billion light-years from Earth. An explosion so powerful, so strange, and so long-lasting that it broke almost every rule astronomers thought they understood about the most violent events in the universe. Gamma-ray bursts, the most energetic explosions known to exist since the Big Bang, itself are supposed to be fast. Most last only a few seconds. Even the longest ones typically fade within minutes. This one didn't fade. It kept erupting again and again for 7 hours straight, and when astronomers looked closer, they found evidence the disturbance had actually been building for a full day before that. It has since been confirmed as the most energetic cosmic explosion ever directly measured by human instruments. Scientists still aren't entirely sure what caused it, and the James Webb Space Telescope, called in to help solve the mystery, only deepened it. This is the story of GRB 250702b, the object some have called truly terrifying, and why, once you understand what actually happened, that description might be exactly right. It's worth noting up front that terrifying here doesn't mean dangerous to us. Nothing about this explosion threatens Earth in any way. What makes it unsettling is something more fundamental. The discovery that the universe is still capable of producing events so far outside our existing understanding that some of the most experienced astrophysicists in the world, people who study cosmic violence for a living, looked at the data and openly admitted they had never seen anything quite like it. Part 1. What a gamma-ray burst is supposed to look like. To understand why this event alarmed astronomers around the world, you first need to understand what a normal gamma-ray burst looks like, and how rigidly predictable they had seemed to be right up until this one appeared. Gamma-ray bursts are the brightest, most energetic explosions in the known universe, capable of outshining an entire galaxy for a brief moment, visible from billions of light-years away. They come in two basic types. Short gamma-ray bursts, lasting less than 2 seconds, are produced when two extremely dense objects, neutron stars or a neutron star and a black hole, collide and merge. Long gamma-ray bursts, lasting anywhere from a few seconds to a few minutes, occur when a massive star, many times more massive than our Sun, reaches the end of its life and collapses inward, its core collapsing into a black hole while blasting narrow, high-speed jets of radiation and particles outward at nearly the speed of light. Both types share one defining feature. They're brief. A star can only die once. A merger can only happen once. The explosion associated with either event follows a well-understood arc: rise, peak, and fade, typically within seconds to a few minutes, sometimes stretching to just over half an hour for the most extreme prior examples on record. This predictability has made gamma-ray bursts, despite their extreme violence, a relatively well-understood category of astronomical event over the past several decades. Astronomers have built detailed theoretical models explaining the physics behind both short and long bursts, tested those models against thousands of observed examples, and generally found good agreement between prediction and observation. It's precisely because this framework had proven so reliable across so many prior events that GRB 2572b's refusal to fit within it registered immediately as something worth taking extremely seriously. GRB 250702b didn't follow that arc at all. Understanding just how rare and violent gamma-ray bursts already are helps put this event in perspective. Astronomers have cataloged roughly 15,000 gamma-ray bursts since these events were first accidentally discovered by American military satellites in the late 1960s, originally built to detect covert nuclear weapons tests. Even among that enormous catalog of extreme cosmic violence, GRB 250702b stood out almost immediately as something categorically different. Not simply an unusually bright or unusually distant example of a familiar phenomenon, but potentially something that didn't fit into either of the two established categories at all. Part 2. The explosion that refused to end NASA's Fermi Gamma-Ray Space Telescope first detected the burst on July the 2nd, 2025. Almost immediately, it became clear that something was deeply unusual. Rather than fading within minutes, the burst kept flaring, repeatedly in distinct episodes for at least 7 hours straight, nearly twice as long as the previous record holder for longest gamma-ray burst ever recorded. That alone would have made it remarkable. But the strangeness went further. China's Einstein probe had detected an associated burst of X-ray emission roughly 10 hours before the gamma rays even appeared, meaning whatever was happening at the source had apparently been building in some form for the better part of an entire day before the main explosive event was even detected. No previously studied gamma-ray burst had ever shown X-ray activity preceding the main event by anywhere close to that long, and it doesn't match the standard models scientists use to explain how these bursts unfold. Researchers studying the event described it in stark terms. One member of the international research team called it an outburst unlike anything witnessed in the past 50 years of studying these kinds of cosmic explosions, a description that, from scientists who study the most violent events in the universe for a living, carries real weight. Adding to the strangeness, the burst didn't simply flare once and fade slowly, it repeated. Multiple distinct gamma ray episodes were recorded from the same source, separated by gaps, then flaring again, a pattern so unusual that astronomers eventually assigned separate designations to different phases of the event, cataloging it as a series of related bursts, rather than a single continuous explosion. That kind of repeated, episodic structure simply doesn't fit the physics of a star that can only collapse once, or two objects that can only merge a single time, forcing scientists to seriously question whether the standard explanations for gamma ray bursts could account for this event at all. Part 3. Finding out where it came from. Before scientists could even begin to explain what had caused GRB 250702b, they first had to figure out something more basic: where exactly it had happened. The burst position in the sky created an immediate complication. It appeared to originate from within the crowded, dust-filled plane of our own Milky Way galaxy, raising a genuinely unsettling possibility that this record-breaking explosion might have occurred uncomfortably close to home, astronomically speaking, rather than in some distant, safely remote galaxy. Ground-based telescopes moved quickly to resolve the question. The European Southern Observatory's Very Large Telescope, using its infrared Hawk-Orange camera, captured images just a day after the initial detection, managing to pinpoint the burst's exact location with enough precision to establish something crucial. This wasn't happening inside our own galaxy at all. It was extragalactic, occurring in a separate galaxy entirely, later confirmed using the Hubble Space Telescope. That distant origin was, in its own way, reassuring. Whatever violence had produced this explosion, it wasn't unfolding in our own cosmic backyard. But pinpointing the general location was only the beginning. To truly understand the explosion's power, scientists needed to know precisely how far away it was. And that's where the James Webb Space Telescope became essential. The urgency behind this rapid, coordinated response is worth appreciating. Within roughly a day of the initial Fermi detection, multiple major observatories around the world, ground-based telescopes in Chile, orbiting space telescopes, X-ray detectors in orbit, had all been mobilized to study a single event. That kind of rapid international coordination doesn't happen for ordinary astronomical curiosities. It happens when researchers recognize, almost immediately, that they may be looking at something that could reshape their understanding of how the most extreme objects in the universe actually behave. Part 4. Webb confirms the most energetic explosion ever recorded. Using Webb's exceptional infrared sensitivity, a research team was able to measure the burst's distance with far greater precision than ground-based telescopes alone could achieve. The result was staggering. GRB 250702b had occurred in a galaxy more than 5 billion light-years from Earth, meaning the light and radiation reaching Earth's instruments in July of 2025 had been traveling across the universe since a time well before our own solar system had even finished forming. Once researchers factored that immense distance into their calculations, they arrived at an even more remarkable conclusion. Accounting for how much energy would be required to produce an explosion this bright, visible across such an extraordinary distance, and sustained for such an unprecedented duration, GRB 250702b turned out to be the most energetic cosmic explosion ever directly recorded by human instruments, surpassing every other gamma-ray burst, supernova, or high-energy event previously measured. To put that distance in perspective, 5 billion light-years is roughly the same order of magnitude as the age of our own solar system itself. The light Webb captured left its source before Earth had finished forming, traveling silently across the expanding universe for billions of years, arriving in July of 2025 as one of the strangest signals ever recorded by human instruments. That single fact underscores just how much energy an event like this must release to remain detectable in exquisite detail after crossing such an enormous stretch of cosmic history. Scientists then searched for what should have been an obvious companion to an event this powerful, a supernova, the visible stellar explosion typically associated with long gamma-ray bursts of this kind. They didn't find one. That absence matters more than it might initially seem. Nearly every well-studied long gamma-ray burst on record has eventually revealed an accompanying supernova, once astronomers looked closely enough, confirming the standard picture of a massive, dying star collapsing to produce the burst. GRB 250702b is a notable exception to that pattern, and exceptions of this kind tend to be scientifically important, precisely because they test whether the underlying model actually holds in every case, or whether it's simply the most common outcome among several possible pathways to producing an event like this. No bright supernova appeared anywhere near the burst's location, despite researchers specifically searching for exactly that signature. It's possible a fainter supernova is simply hidden behind the thick dust of its unusually large, dusty host galaxy, one of the biggest and brightest galaxies ever found, hosting a gamma-ray burst. But the absence of an obvious expected companion explosion left the true cause of GRB 250702b stubbornly uncertain. Part 5. What could actually cause something like this, with the standard explanations, a straightforward collapsing star or a simple merger, struggling to account for everything observed? Researchers have proposed several genuinely unsettling alternative explanations. Scientists studying this event have had to seriously entertain the possibility that GRB 250702b doesn't fit neatly into gamma-ray burst physics at all, and might instead belong to an entirely different category of astrophysical event called a tidal disruption event, the specific, violent process by which a black hole gradually shreds a star that has wandered too close, stretching it into a thin stream of material before consuming it. Tidal disruption events can indeed produce sustained, repeating flares of radiation over extended periods, unlike the single, brief burst typical of a star's core collapsing. If that's what happened here, GRB 250702b may represent one of the clearest examples yet of this particular class of cosmic violence, observed with a level of detail no previous event has offered. One leading possibility involves an elusive, rarely confirmed class of object called an intermediate mass black hole, significantly larger than the stellar mass black holes formed by dying stars, but far smaller than the supermassive black holes found at the centers of galaxies. Some researchers believe GRB 250702b might represent a star being violently torn apart after wandering too close to a black hole of exactly this intermediate size, a scenario that could plausibly explain both the extreme energy involved and the burst's strange, repeating, extended structure, closer in some ways to what scientists call a tidal disruption event than to a classical gamma-ray burst. Other researchers have proposed that the event might represent an entirely new category of ultra-long gamma-ray burst, potentially tied to the collapse of an unusually massive type of star called a blue supergiant, a scenario that some existing models suggest could theoretically produce sustained accretion onto a newly formed black hole lasting anywhere from tens of minutes to several hours, though even this explanation struggles to fully account for the day-long buildup detected before the main burst. Intermediate mass black holes, the other leading candidate explanation, occupy a strange and still poorly understood place in astrophysics. Scientists have confirmed the existence of smaller stellar mass black holes formed from collapsing stars and much larger supermassive black holes found at the centers of most galaxies, including our own. But black holes in between these two extremes, ranging from roughly 100 to 100,000 times the mass of our Sun, have proven remarkably difficult to confirm directly, with only a small handful of candidate detections in the astronomical record. If GRB 250702b does turn out to involve an object in this category, it would represent one of the strongest pieces of evidence yet for a class of black hole that has largely remained theoretical. Follow-up observations using Webb's ANIRCam instrument conducted several months after the initial explosion added yet another layer of uncertainty rather than resolving it. Researchers examining the host galaxy in unprecedented detail found a single, extremely large, structurally complex galaxy, one so intricate that scientists still aren't entirely certain whether any trace of the original explosion even remains visible within the data, or whether it has already faded below the threshold of detection entirely. Part 6. Why scientists are taking this so seriously. It's worth being clear about what makes an event like GRB 250702b genuinely significant, rather than simply strange for its own sake. Gamma-ray bursts represent some of the most extreme physics anywhere in the observable universe, testing the absolute limits of how much energy nature can release in a single event, and offering rare, direct windows into processes like black hole formation and the death of the universe's most massive stars. Beyond the immediate mystery of what caused this specific event, GRB 250702b has practical implications for how astronomers plan future observations. If ultra-long, repeating gamma-ray bursts like this one turn out to represent a previously unrecognized category of cosmic explosion, rather than simply an extreme outlier within existing categories, it means observatories around the world may need to reconsider how they monitor the sky for these events, potentially catching similar bursts earlier and studying them more completely the next time nature produces one. An event that breaks the established rules this dramatically, lasting hundreds of times longer than a typical burst, preceded by a full day of unexplained X-ray activity, and apparently missing its expected supernova companion, forces scientists to seriously reconsider whether their fundamental models of stellar death and black hole formation are actually complete. Every instrument capable of observing high-energy transient events was rapidly turned toward this single explosion, specifically because researchers understood, almost immediately, that whatever had happened didn't fit cleanly into any existing category. That kind of scientific urgency, mobilizing observatories across the globe within hours of an initial detection, is reserved for events considered genuinely important, not simply unusual. The comparison to the previous record holder is instructive. Before GRB 25072b, the longest gamma-ray burst ever recorded, designated GRB 1.209a, lasted roughly 2.5 hours, itself considered an extreme outlier at the time of its detection in 2011. GRB 25072b didn't just edge past that record, it nearly tripled it, while also displaying a repeating structure and a day-long precursor signal that GRB 1.209a never showed. In the world of extreme astrophysics, where records tend to be broken by modest, incremental margins, an event that shatters the previous benchmark this dramatically, while also introducing entirely new characteristics never seen before, understandably commands serious scientific attention. Closing is GRB 25072b terrifying? In the sense that it poses any danger to Earth? No, it occurred more than 5 billion light years away, so distant that even its almost unimaginable energy poses no conceivable threat to anyone here. But in a deeper sense, it's a genuinely unsettling reminder of how much violence the universe is still capable of unleashing, and how incomplete our understanding of that violence remains, even with the most powerful telescopes humanity has ever built, trained directly on the event as it unfolded. Somewhere in a distant, dusty galaxy, 5 billion light years away, something extraordinarily powerful tore itself apart, repeatedly over the course of an entire day, defying every model scientists had built to explain how such explosions are supposed to behave. The James Webb Space Telescope confirmed it as the most energetic explosion ever directly measured. It could not, however, tell us exactly what caused it. There is a particular kind of unease that comes from encountering something the universe has clearly been doing for billions of years, that we are only now, for the first time, equipped to actually see and measure. Gamma-ray bursts of some kind have almost certainly been occurring since shortly after the earliest stars in the universe began forming and dying. GRB 25072b isn't a new phenomenon in any cosmic sense. It's an old, perhaps common category of event that we are only now, with instruments as sensitive as Webb, finally capable of studying in enough detail to realize how little we actually understood about it. That answer, for now, remains one of the most compelling open mysteries in modern astrophysics. A genuine unknown, hiding in plain sight, radiating out from a corner of the universe far beyond anything we can currently fully explain. Researchers continue to comb through the data collected in those crucial early hours and months, searching for the clue that will finally tell them, with confidence, exactly what kind of catastrophic event they were lucky enough to witness.